Um, um, thanks for the nice introduction, and thanks everyone for attending. And I kind of feel responsible for being a last speaker. I would like to thank Valerie for organizing Cafe of this semester. And let's start. Yeah. So today's talk I'm gonna present is what it's on the title: minimal no interpolation by perceptual explicit regularization and implicit bias, which seems to be tons of those buzzwords. But I'm gonna explain later. And this is joint work with Ian Pelek at Iowa State University and Dr. Stefan Wojtowicz, who was previously in Texas A&M Math Department, and now he's at University of Pittsburgh. So for today's talk, I'm going to introduce kind of general motivations and some preliminaries. And instead of like focusing on my kind of technical details, I would like to just give you some big picture of how this field goes and just like what kind of problem, why we need to solve these kind of problems. And so these are in the introduction. And on the main, I'm just briefly introduce our results and like application of our results. And I'll make a conclusion. And if time permits, I have all the technical details in the appendices. And as I just mentioned, these very technical details. So like, if you are not interested in this part, you can feel free to leave. So I would like to start from general motivation about like why we study something kind of called the perceptron. And like some people call it two-layer neural network. Some people call it shallow neural network. Some people call it perceptron. And indeed, perceptron in my title was just plural of this perceptron. So like, I'm going to use mix. I'm going to not distinguish these words. So I'll sometimes say shallow neural network. I sometimes say two-layer neural network. So why we need to study this kind of two-layer neural network? Like everyone, I think everyone in here should agree that like we are kind of in the era of deep learning. So why we need that shallow neural network? So like many people would have some like different motivation from each taste, but personally, I think the reason we study this kind of model is because it's a kind of tractable model for theoretical analysis. So like, as many of you know, like deep learning is like hard to analyze in theory, like we don't really know how it works exactly. So like, it's simple. So we are starting from the simple model. So like, for example, one things we can learn from this shallow neural network, what we can obtain from shallow neural network is what a concept called the implicit bias, which was also in my title. So what this implicit bias means is like how the model setting of the neural network, for example, how you choose the activation function, how you choose the depth of the neural network, like which optimization algorithm you will use, like how those model settings will affect the solution we obtain. So this term implicit bias comes from these kind of model settings kind of implicitly give you some bias towards a certain solution. Like, yeah. And the other thing I think we are able to get from this study of shallow neural network is what the concept calls depth separation. So like this means like we are interested in this kind of problem. Like we know deep learning works powerfully, but like how deep neural network we need, those kind of things are still in veil. And so we want to answer this kind of question. What kind of problems are solved with shallow neural, like what kind of problems are sufficient to solve with shallow neural networks? And what kind of problems are needed to be deep neural network? To answer this kind of question, we need to first know what kind of problems we can solve by shallow neural network and what are not. Oh yeah.
How to define shallow and deep?
Oh, that's what I'm going to introduce in the next slides. Thank you for mentioning. And yeah, I forgot to mention that feel free to interrupt me whenever you guys want to have a questions or comments. So to that end, to answer Dr. Ning's question, we will first start with defining general neural network. So neural network is the function of having the following like function compositions. This HK is some function that is here is a affine transformation inside, and some weird function called sigma is composed with this affine transformation. And you have a K, large K, H's, and then G at the last. So this W term is called the weight of a neural network. And B term is called the bias. This bias is totally different concept with implicit bias we have discussed. It's just, this one is for just theoretical definition, and implicit bias is more like just general words. And this sigma is a function, and we predefine the function with a non-linear function, which is called an activation function. An example of this sigma, we have a tangent hyperbolic, for example, and ReLU, which has this kind of form. So it's y equal x at the positive side, but it's 0. You truncate to the 0 for the negative side. And from now on, like in this talk, we'll stay with the sigma activation function with ReLU. And G is called like the final layer. It's not widely used widely used lexicon, but and this G is just to convert the neural network output into a desired form. For example, if you want to do the classification, you want the probability as a last result so that you can choose the highest probability. So like in that case, like G is just a softmax function. And if it's we are doing some regression, G is just a linear map. So each HK is called a layer. This one is called a layer. And this DK is called the width of K layer. And that large K entirely is called the deep, is called the depth. So everyone's good with this definition? So yeah, and why we are using this kind of neural network, and there is some theoretical guarantee that is called universal approximation theorems. And I intentionally put S there to denote that this theorem is not a certain theorem, but this kind of bunch of theorems. But most of them, those theorems have a different condition on required depth and required width and those kind of the choice of activation functions. But most of them just generally states that any continuous function with compact support can be approximated by a neural network with suitable width, length, depth, and activation. And what I mean approximated by is with respect to the subnorm topology. So it's a uniform convergence. And so in more mathematical words, the set of neural network is dense in CK with respect to supremum topology. So this universal approximation theorems kind of gives you a guarantee that if we want to get any function, any continuous function, we can use neural network. And so there are variant versions of these universal approximation theorems depending on the condition, as I just mentioned, but most of them has the same limitations. So compact support is necessary, and it's kind of, you can infer from we require that uniform convergence is required. And they often lack the quantitative bound. What I mean quantitative bound is we know it approximates, we know it converges, but we don't know exact rate of convergence. Or if you have the rate of convergence, it's not most of them are not very tight bound. So, and mostly they focus on this primum norm topology. So these are the theoretical guarantees to use the neural network. But as we just mentioned, some of them are not very kind of desirable. But in shallow neural network cases, these limitations can be kind of resolved, and this is the one of the contribution of our paper. So now I'm moving to the shallow neural network. Is there any question for general neural networks? Sounds good. So now I'm moving to the shallow neural network, and shallow neural network is the function of now two-layer neural network. Is now you have as you just mentioned, we have a one layer and one final layer to make a desired output. So, and 1 over m is just normalizing constant, it's just a constant if we fix m. So it doesn't matter. And m is now a width because we have only single layer, we have only single width. And like the question we want to ask is which functions can be approximated well by two-layer relu neural network? As we just mentioned, like what we want to solve is like which problems can be solved well by shallow neural network. To that end, we want to check like whether shallow neural networks are also sufficient to approximate any functions, or there is a function that they cannot like approximate well. So to that end, we want to check, we want to see like, so like in here, we want to check whether this can approximate well. And what I mean by approximate well is that if you have infinite number of parameters, then it can, how much it can express the entire like function family. To that end, we want to make some kind of continuous extension of this form, right? So what we are doing here is that check that this is indeed like if you think parameters as some kind of sample, these are just sample means over the parameters, right? If you fix X, so that you can change it to this kind of expectation form with respect to these M atomic measures. Then like as like we all know that its generalization would be this any some kind of measure can be approximated by this form, right? M atomics. So it's expectation over pi, and with respect to pi is a distribution of parameter. So these are the kind of continuous extension of this supine M width two-layer neural networks. Oh yeah.
Just the two-layer neural network, you already have M of A and M of W and 1B.
Right.
So this is 2M plus 1.
Yeah.
Dimension. Okay.
Yeah. Yeah, 2n plus 2. Yeah. So like, so W has a D dimension indeed, because like X has a D dimension, we will assume. So it's RD and it's R. So it's RD plus 2 dimension. And we have M parameters of them. So this data space is RD plus 2. And we have M samples of them.
What's the dimension for A?
A is just A. So in AJ is M dimension, but if you have a continuous extension on A, like your A is just a real number.
So you here A is a vector.
No. A is just a real number.
Oh, okay. This A is M dimension. Before is A is for the
Yeah. So
G.
yeah,
so it's M dimension. And then W, what's the dimension of W?
W's dimension is RD. Like
R
D.
times D.
Yeah, D is dimension of X, and W's dimension is RD.
R times D.
No. R's D power of D.
R is the power of D.
Yeah. Yeah, it's D dimension, sorry. I should mention something like that.
W is the D dimension.
Right.
And what's the dimension of B?
B is just a real number again.
Real number. So it's M plus D plus 1. That's the dimension of the parameter.
So first of all, if like forget about this M thing, and if you only look at this thing, you get a real RD vector. You get the D dimensional vector, and returns a real number. So this is a D dimension, and you inner product with D dimensional vector. So W has a D dimension D, and B is now this is a real number. So this is a real number. So you have so this is a real number, and this is real number. So theta lives in RD, yeah, D plus 2, but we have M samples of theta.
Oh, okay.
Thanks. Any other question? And now we denote this like curve B as functions that can be represented in this form with some measure pi. Note that this representation is not unique, that like you can have a multiple pi satisfying the same f, but we're not gonna care about it because like in next slide, that's where we can resolve those things. We can assign a natural norm in this B, which is called the Baron norm. And as I just mentioned, like one function can have multiple representation of like by changing the measure of the pi. But we're gonna take an infimum over them. And this is just, now you skip the activation function and export, and you just make a W plus B, and you take an infimum of them. And this is known to be a norm. Like you can check, it's not very easy because like you have those like integrals like decomposing an infimum, but it is a norm. And so this B comma norm B is indeed the Banach space. We can check that it's indeed complete in two. So we call this space a Baron space. And Baron space is a function. So Baron space is a function that can be approximated well by perceptra. So in other words, perceptra is dense subset of Baron space with respect to Baron norm. So our question was this: which functions can be approximated well by two-layer value neural network? And our answer is Baron space. So any questions? All right. And I just want to make remark here that's not on the slide, but like, but when you think of approximation, like, of course, like we have nice theorem that neural network can approximate any function. But in practice, we are interested in like we have multiple approximation methods. For example, linear regression is also one method to make an approximation to a function. And indeed, indeed, the thing I kind of omitted in this slide is that we have to compare the quality of approximation, because like even though neural network can approximate well, if for example, linear regression can work better, why do we need to use the neural network? And indeed, this Baron space is kind of intentionally built for this two-layer neural network. And this space is defined because we want to make some space of functions that can be only approximated well by shallow neural network and not by kind of just linear approximation. Oh, okay.
Can you locally characterize a function which can't be well approximated by the set of? I don't really.
Oh yeah, that's kind of thing I wanted to introduce next slide. So yeah, thanks for mentioning this. Yeah, so like up to this part, we make a nice conclusion. Baron space is the function space that can be well approximated by perceptra. But as Alex mentioned, it doesn't give us any information. So what is the Baron space? It's just we just make a continuous extension and see this is what we can approximate. But what about that space? So we need some information of this space, but luckily we have some results from the other literature that Baron space indeed has a relationship with other function spaces. So we can borrow some of the functional analysis theories to analyze the Baron space. For example, if the data has a boundary support, this Baron space is known to include all the Sobolev space with a sufficient dimension, which just means that you have a sufficiently smooth function. So like if smooth enough, like all smooth enough function can be approximated well by Baron function in the Baron function. And also, for those of you who might be curious about details, this intuition comes from the fact that this Baron representation, if you substitute the sigma to the activation function to some kind of Fourier transform, e to the minus itx kind of thing, and you think the theta as a parameter space, I mean, frequency domain, it resembles kind of Fourier transform. So, and this norm is indeed kind of motivated from the Sobolev norm in the Fourier dimension, Fourier space. So that's how you get this kind of result. And also the other thing known is that this Baron space is included in the Lipschitz function space. So Lipschitz function space is larger. So we know two things. So Baron space can include sufficiently smooth function, and all Baron functions are Lipschitz function. So that kind of answers Alex's question. So some like non-Lipschitz functions cannot be approximated by Baron function, for example. Oh yeah.
It's about like, can you go back one slide? So thank you. Sorry, one more slide. So in the use of observations, because I use that and then you go to fix sigma to be the value.
Yeah, sigma is fixed to be value.
Well, it is because like A to A Because the max is the max of zero times the linear functions, like multiply constant contribution.
No. So you said A is redundant because you can move into A, right?
So max of A times max of zero base is just like the max of zero.
Right, but if A is a negative number, if you put it inside, yeah, then it's zero. But we
And what I'm saying is like here A, okay, yeah, then you just assign A.
yes, yeah, indeed, that's a trick we will use in the proof. So like we only need the sign of A indeed.
Yeah, because it's just like a matrix, it's not really.
Oh yeah, but yeah, right, because we already have 1/m there.
Yeah.
Right, correct. Yeah, it's definitely correct, and that's a trick we'll use in proof. But
Okay, so and another question here, another question that can you go to relationship space, relationship
Yeah.
space?
Yeah.
So so you mentioned some examples for different choice of like size, so different choice of segment.
so no, this is not something like different choice of sigma, but this is just a motivation. Like if you think sigma is a cosine function, then it's a Fourier transform. So it's
Like if this well, then what's the phi space?
so that's the Baron space, and so
Yeah,
that
but then what's okay? So then the first bullet point is
Mhm.
okay. I see. So you say like so the second bullet point is actually another space.
yeah.
Then the first bullet point is already
No. So like this is just to give an intuition that like how this why this Sobolev norm is like related to the Baron norm. And like if you fix sigma as a cosine, then this is indeed Sobolev norm, and this is indeed the Fourier representation of F. So like it seems like there's some relationship, but we have a different activation function. So definitely it's not a difference. It's not a yeah, sorry about it.
If I know that right, that's what you say is that the relationship.
Yeah.
First one actually holds.
It's
For your parents.
so yeah, it's totally different story, but just to give you an intuition, and this intuition indeed originally what Baron thought. Yeah, that's why I just included here. Yeah. So like we now have everything good. We know shallow neural network can approximate Baron space, and we at least have some information about Baron space. So it seems like everything is good now, right? But there must be a reason I put this question here because it is not. So so like up to this part, theoretically, it's nice. We have some nice Banach space, and we know some tools to analyze that Banach space. But note that this term again, we have this norm. Remember this term, and there is a B part here. You have a plus B here. And indeed, it turns out that this B is quite problematic in practice. So like theoretically, there's no problem, but there's some discrepancies between the practice. So Baron norm, if by including the bias term in the norm, it's not invariant under the translation of data space, or like in other words, location shift. And like in many deep learning kind of context, people like, for example, if you want to do an image analysis, you first center the image and do some analysis. Those kind of practices are common. But by having a B term, we have some invariance under the translation. So that it's like if you shift the image and then do everything, now it has a different Baron norm. So it's kind of problematic. We are solving same task, but we are having a different function. Also, this bias term has no contribution to overfitting. What it means by like is that, for example, think of Ricci or Lasso regression in our case. Those regularization have kind of multiple use. Like for example, Lasso is for like variable selection or those kind of things. But mainly also what they do is you kind of prevent the overfitting. So like if you train the neural network very intensively, you will learn every data. But in that case, if you have a new data, then they do not perform well. To that end, we add some kind of regularization, for example, Ricci or Lasso, those kind of things, to make to prevent the overfitting. So what we want is similar here. So like the Ricci or lasso is basically penalizing some norm of the parameter. And you can think this as a normal parameters too, right? So like we want to do similar thing. Can we penalize by the borrowed norm? But like in that case, what happens is that bias term has no contribution to overfitting. So like we don't need to control the bias term in that case. So we want to make some regularization like Ricci or Russell, but without controlling the bias term. But if we include the borrowed norm, we automatically control the bias term as well. So these two are kind of not desirable in practice. So what we in practice use is a weight decay penalty, which does not include the B term, but only the A and W term. So like it's kind of indeed backward. I introduce every theory and there's a discrepancy between practice, but it's indeed backward. We already have this weight decay norm in using, but as we develop the theory, it turned out that it doesn't match with what we use in practice. So like then theory is always something to explain the practice. So we want something similar to this instead of like our theoretical kind of foundations. So is there any concept corresponding to this weight decay regularizer? And as we just did in Baron space thing, we also make a continuous extension, which would be something like this by same logic. Then I denote it as a bracket B, but this bracket B is not a norm, but a semi-norm not a norm because you don't control the B term. So it's trivially functions have different B's would have the same Baron semi-norm. So we call it Baron semi-norm or sometimes weight decay norm. And by using the Baron semi-norm, we can not only we can fit into the practice, there are some benefits in theoretical as well. So like for any f with bounded at 0 and Baron semi-norm is finite, is also a Baron function. So it's kind of like if you only control at the origin, it will almost work same with Baron space. And if function is in Baron space, then I said every Baron function is a Lipschitz, and its Lipschitz constant is bounded by Baron semi-norm. So aggregating these facts, we can think that Baron semi-norm is not that different with Baron norm. So our theory in Baron norm kind of would work very similarly. And just to last remark, in my title, there was a minimum norm interpolant. And what it means is the function that minimizes the Baron semi-norm under the data fitting constraint. So it fits the data and interpolates the data by minimum Baron semi-norm. So so this was our preliminary. And is there any questions so far? Sounds good. Then since I introduced main ingredients, so now I want to have what is our main question in this work. So main questions addressed in this work is, can we obtain the approximation error between two-layer ReLU neural network and target function? And we want to have an approximation rate with explicit approximation rate with respect to number of parameters and weight decay regularizer and number of data. And we want to extend that result into what we mentioned in the restrictions of universal approximation theorems. We want unbounded and non-Lipschitz laws and non-compact kind of data support, and which will assume a sub-Gaussian. And how the two-layer ReLU neural network, suppose we fit the data well, then how that neural network interpolate where there is no data? That's another story. And lastly, if we obtain some theoretical results, what can we use that to analyze, for example, what I just mentioned about implicit bias? For example, how we can compare the different learning schemes, whether which optimization algorithm has which kind of implicit bias. those kind of things are will be answered in our next part. Yes.
Still back to my first question. I still don't understand how is the criteria to tell if a neural network is deep or shallow. Like if it's like only less than 5, is it shallow, or is it above 5 is deep? What's the how to tell?
So like this 2-layer is shallow neural network, and anything deeper is deep.
What?
Anything more added.
Okay.
If you add any more layer, we call it deep.
So it's a capital K bigger than equal to 1.
Yeah, bigger than capital K larger than 1 is.
Bigger than 1.
Yeah, it's deep.
That means only H1 and T as this 2 layer.
Yeah, that's exactly this one.
H1 and T is the 2 layer. And if it's K bigger than 1, like a 2, that will be 3 layer.
Yeah, right. Thank you. Thank you, because we have H1 and G, so that's why we call 2-layer. So sorry about the confusion. So like to answer these questions, now I'll just introduce some notations. These are just notations. So X is a data distribution, and mu is data distribution, and which assumes that norm of X is a sigma sub-Gaussian, and N is a data set size, and M is a width of neural network. We are shallow, so we have only one width. And lambda is, I think it would be better to explain these first. So F star is a target function we want to train. And we express the 2-layer neural network as the following. And what we will have a target loss function is this kind of quantity, which is L2 loss. We analyze the MSE loss between the F theta and F star. And you add a weight decay regularizer as like what we do in practice. And this lambda is now a strength of weight decay regularizer in this risk functional. And Fn, we will have everything with respect to n. So it's for given data, this minimizer of this empirical risk functional, I'll call it ERM, like empirical risk minimizer as an ERM. This Fn is with respect, with a given data, what is a minimizer of this? And this bracket B denotes the Baron seminorm we just mentioned, and it's so I think since we make all the notation clear, now I'm ready to introduce the main theorem. So if M and lambda scales appropriately with respect to n, so it's not too small, it's not too large, and with respect to n and parameter, then Fn, the empirical risk minimizer, converges to some function f infinity in LP and uniformly on complex subset. But what this f infinity satisfies is f infinity is f star mu almost everywhere. So it means we fit the data exactly. And it has a less or equal Baron seminorm than f star, which is what I just called about the minimum norm interpolation, because like if you fix any f star with the minimum norm interpolation, f infinity would still have a less or equal norm. And explicit L2 bound between Fn and f star is expressed the following. I'll explain about this in the later slides. So comparison, I'll just first start with like what we have improved. So we used the general sub-Gaussian data instead of complex support data. And we did not control the magnitude of bias variable as I just mentioned. And we used the theory for the L2 loss, which is widely used, but this L2 loss is not Lipschitz, so it's turned out to be very problematic indeed. But our results can be applied to L2 loss. And like we also characterized like so mu almost everywhere we fit the data. But what happens where there is no data? We explained that even if you converges uniformly on complex subset, even if there is no data. So this explains the minimum norm interpolation behavior. And one thing to note is that the reason I wrote this kind of complicated statement is because this F infinity may not be unique. So like we can have a different F infinities, but having this satisfying this property and fitting the minimal norm interpolants, because minimal norm interpolation itself is not unique. Oh yeah.
Your inequality in your assumptions for M and M, which basically means that you actually have to have tuning separation between those. So like, it's not enough for lambda to be, you know, a little bit bigger than logging over through that, but it has to be like 5%. And like, if you imagine that lambda is indexed by n, are you requiring the balance there to be non-trivial in the S? So I understand the double inequality types.
Oh yeah, double means the rate of, like asymptotical order. Oh, sorry, is it clear?
That does.
Yeah, sorry. So this double inequality means I'm having everything in asymptotic sense. So like I want to give some analysis of the bound. So why these bounds kind of came. So this first 1/m term comes from by constructing some. So like we have an empirical risk minimizer, and we have a true function. But between them, what we'll do is we'll construct some like theoretically ideal neural network approximator of the true function, which may not be a risk minimizer. So here's the Fn, which is a minimizer. And here is the F star, which we want to really make. But like this is a minimizer of ERM. I mean, ERM is also a minimizer, sorry. This is a minimizer, but ideally, need not be a risk minimizer, but there should be some function that's approximation. So there should be some function. It's a neural network, and it approximates F star well, but may not be a risk minimizer. So like indeed, what we want to do is we want to make this as close possible. And if this and this is close enough, then we will have this and this close enough. So that's kind of our strategy. So this 1/m terms from constructing the such F theta tilde. And this log n over square root n comes from sub-Gaussian condition and radiometric complexity of two-layer ReLU neural networks. And lambda term comes from the weight decay regularizer at the last time. And like some people might wonder why there's no dimension thing, and that's indeed hidden inside the norm of x square and sigma square, because like we assume them to be just sigma sub-Gaussian, but indeed like those sub-Gaussian parameters often depend on dimension. And we want to make a notice that this bound is not sharp, so indeed there's some chance of improvement in this bound. So any questions here? Okay. So this theorem now gives us some results. First of all, we know how well it approximates with respect to m and n and lambda. And by scaling lambda and m appropriately, we know like with the fixed data, how much error we will obtain. Because these conditions will give you quantity with respect to n in overall. And so our error is bound if we have the data, at least asymptotically, we know how the error is bounded with respect to number of data size. And second, we know the minimal norm interpolation behavior. So we have some theoretical results here. And the matter is now how you can use these theoretical results. But as I just mentioned, as I just give you a teaser, we'll use to study the implicit bias. And the fact is because there is no guarantee that so we have obtained a very nice theoretical result, but in practice, what optimization algorithm do is find a local optima But now all our analysis were given we find the global empirical risk minimizer. So there is no guarantee that these two matches, like one we actually trained and one we theoretically have. So like in practice, it's very hard to analyze the theoretical perspective on your like aspects of neural network because we don't know what is a global minimizer. But in our case, we know what is a global minimizer. So we can compare the global minimizer to our actual solutions and find out why we have a deviation between local optima and global optima. So that's kind of strategy we will take. So especially in the case of minimal norm interpolant is known, we know exactly what functions we want to train, and we can compare why local optima does not find this kind of thing. So example of known minimal norm interpolants are two things. First of all, convex data in one dimension. I'll explain what it is later. And second is radially symmetric bump function in all dimensions. I'll also explain this later. So convex data in one dimension is first example. Do you have any questions so far? Okay. So convex data in one dimension is first thing. So in 1D, when I say 1D, it's a data. Any convex function is a minimal norm interpolant of convex data indeed. That's kind of, so we have a large class of families. So we just considered f star x being absolute to x with data lying between 1 and 2. So these lines are where we put the data, and we want to train that y equal absolute to x, and we see how they interpolate this region where they have no data. And if you check, and if we did not include the weight decay regularization, surprisingly, if you initialize the parameters small, they all fit the convex function. So even though we didn't penalize any weight decay or Baron semi-norm, they still find the minimal norm interpolant in small initialization case. But in this large initialization case, you can clearly see that these functions are non-convex. So like this like scheme of initialization is kind of often neglected in neural networks training, but these gives very critical like implicit bias towards the minimal norm interpolation or not. So this is one observation. But like here, if you add the regularization, you can check that now, even in large initialization, you can still fit the convex data. So this is the first observation we have. And second example is radially symmetric bump function, which means that f0 is 1. And outside of unit ball, you have a 0 everywhere. So it's a function, something looks like this. So you have a 1, and you have some kind of bell shape. So outside of unit ball, now you have zeros. And radially symmetric means that it's all same with radial directions. So in that case, what is nice is that since it's radially symmetric, now, I mean, what it means is that if you have, for example, this x where norm is 1/2, then around this circle, every value is same. So what we can do is we can just plot the value of function only by norm of x if we have a radially symmetric function. So that's a nice thing. And if we consider this radially symmetric bump function, there exists a unique radially symmetric minimum norm interpolant for all dimensions. Like this is theoretically known, but one thing I have to make a remark is that it's unique only if we assume radially symmetric function. So if you have a symmetricity with respect to radial directions, it may not be unique. There might be multiple minimum norm interpolants. So given this data, we trained the neural network and we compared with its known minimum norm interpolants. So this pink is minimum norm interpolants, actual theoretically known one. And these are what we found in practice with using the optimization algorithms. And if you can see that these all fits the function well. So, but this one is what is a radial standard deviation. And what it means that like you measure the standard deviation with respect to radial direction. And so that it means what it means is if it's larger, it means that we are not having radially symmetric function. If it's a small, we have a radially symmetric function. So surprisingly, what we found is while SGD and SGD momentum algorithm has a low low radial standard variation, Atom apparently shows much higher radial standard deviation. So Atom and weight decay regularizer, we also measured the value of it. And it turns out that Atom tends to deviate much far from minimum norm interpolation, while other optimization algorithm reveal much smaller. So like so to summarize, Atom is not preserving radial symmetry, unlike the other algorithms. And they do not give implicit bias toward minimum norm interpolation, apparently. Like for atoms that asymmetry with respect to radial direction, there was already it is widely kind of discussed by people that atom is not likely to preserve the radial symmetry, because if you see the atom optimizer update, you can check that you have a squared term here, and you normalize coordinate-wise both. But like in practice, if you want to make some kind of vector second moment and vector normalization, you need to indeed have some kind of matrices here. So that's where you now have some deviation from, okay.
You look at all of the Adam W.
Oh, that's on appendices, but yeah, that's on appendices, but I didn't kind of, we didn't kind of, sorry, I cannot recall the exact simulation results for the Adam W. Yeah. I cannot remember exactly whether they preserve symmetry or not, sorry. So as look at this case, like Adam updates coordinate wise, so which may not preserve some radial kind of symmetries. So it is widely discussed, but as far as I looked up, I could not find the precise kind of literature that really verified that it is really a symmetry. But so I think up to my knowledge, I think we are the first to kind of really verify the Adams asymmetry, but I didn't put that on slide because I want to be some conservative. So at least for this asymmetry, we know that we have some intuition, and we were able to kind of verify these intuitions are kind of correct empirically, at least. So these are the kind of possible application we might use to study implicit bias for our using our theoretical results. So to summarize, first we obtained the convergence of two-layer ReLU neural network ERMs, and with a precise rate, and in case of unbounded support and non-Lipschitz loss. And we also proved minimum norm interpolation behavior, especially even though we don't have any data. And we demonstrated that no minimum norm interpolants can be used to study implicit bias in optimization. And as an example, we used this theoretical result in one dimension case and radial symmetric bump function case to see that some kind of certain conjectures are kind of empirically can be verified. And further works, I'm considering like generalizing and sharpening the bound with different activations and obtaining sharper rates for different norms. And this, I would like to acknowledge that this work is partially supported by the NSF. And thank you.
Do you use the stochastic gradient descent?
Oh yeah, SGD. Here we use SGD.
Okay, but the analysis.
No. For analysis, we didn't consider any optimization algorithm. We are just assuming the minimizer
Oh.
and like what is the property of the minimizer.
And how your result is useful in practice to use.
Oh, so that's like, so two things. What if you're mentioning something about really like truly algorithmic sense? I don't think it's not kind of that useful. But as we just mentioned here, like for example, if we want to check some implicit bias, like if we want to know kind of what is implicit bias of certain optimization algorithms, like our result now gives like at least theoretical solutions, so we can compare, like because many neural network things doesn't even know what is the solution we need to obtain. So even if we obtain some solution from numerical algorithm, we don't know about them. So we don't have nothing to compare with, but now we give some comparison, yeah, kind of controlled group, some kind of, so that you can compare with numerical solutions and theoretical solutions.
So all the stochasticity came from the sample.
Yeah, exactly. Yeah, that's indeed a very critical point. So, yeah. Any other question?
You mentioned in the appendix you had some. I know Adam W was sort of made to correct some problem with the way that they determined the Adam. So I'm curious if that was the issue that needed to be operated.
Oh yeah, I'll check the paper and tell you later.
So for your result without classifications.
Oh, which one?
For your results that the equivalent result that without any classifications.
Any out, yeah, without regularization. This one?
Your model only chance. I mean, does the training error goes to zero?
Training error goes, yeah, like, yeah, close to zero. Yeah, it's kind of parameterized indeed. Yeah.
So, I mean, like, this seems to all sound very complicated to understand. And I don't know, so because like for linear network, like people know that actually for sport, there is a big difference between sport interpretations and numerically.
Yeah, right.
For large representations.
Right.
For large illustrations, like you will have a super long type of just like very similar to rich expressions.
Right.
For small interpretations, sometimes actually something else. So, so like it seems to be, we seem to be getting something different from that because I usually the large transition that actually make
so like I think the matter is which norm you are mentioning at first, because like now like
so, and another question is that I'm not sure whether you are aware of that there are some recent results that actually show that implicit organizations might not be, unless for very specialized network, they might not be explained by long organizations.
long what?
Long regularization.
Low regularization.
Cannot be represented by long regulations. So there are a few works recently that those are the message that actually talk about that cannot be represented by long regulations.
What can be represented?
The implicit regularization cannot be represented by a long regularization.
Oh, okay.
So that's why long it's not the best explanation.
Right. Yeah, we're not saying linear norm interpolation is the best one. Like we want to like. Oh yeah, right. Oh yeah, right. Yeah, I totally agree. And so like implicit bias, like implicit regularization has kind of multiple, as far as I understand the question correctly. So like our minimum, like our study is just to check one implicit bias about minimum norm interpolation, and like it doesn't tell every implicit bias.
What's interesting is that like the work groups seems to agree on that, like agree on your normal regularization indeed. I mean, I'm talking about.
You mean?
I'm look at the pin block data.
This,
So, the result seems to align, the result seems to suggest that the regularization really non-based.
implicit regularization is,
It's really non-based. It seems that it suggests that.
Uh-huh.
We can take it offline.
oh, yeah, sounds good, sounds good. Yeah. I see.
And the